Okay, well, thanks for your time and attention today. My co-authors and I are going to present this case study where we used the new multivariate conditional simulation tool, applied it to a geometallurgical problem for one of our clients. Okay. So my co-authors, Matthew Field, completed his PhD in conditional simulation. He was peer reviewer for the project, but was pretty heavily involved throughout the process, especially at the end with post-processing. And Cecilia Artica, she set up most of the process and ran all the multivariate EDA for us, but unfortunately then she left Mining Plus. So I had the honor of taking over from her, which was great because it's a really exciting project and had a lot of fun with it. So framing the problem, the client has a bio-oxidation processing plant. The plant has been experiencing low recovery events linked to high variability in the deleterious variables. The mine has been unable to predict the deleterious variables in the mill feed as no reliable model existed. The deleterious variables included in the scope for us were arsenic, total sulfur, total carbon, organic carbon, and total iron, which showed positive and negative linear relationships with each other, plus some nonlinear relationships. Standard estimation methods would have smoothed the distributions of these variables, which would also destroy the observed interrelationships. So that's where we turned to conditional simulation. The client needed a model of the deleterious variables that preserved the observed interrelationships so that the following questions can also be investigated. What would be the expected variability in deleterious variables month by month, and how can the feed sources be blended to reduce this variability? If there is a high probability of a threshold for one variable being exceeded, what is the probability of another threshold being exceeded at the same time? Should the BIOX process be modified to handle different feed specifications than current design? And what sample spacing is required to adequately characterize the deleterious variables? After playing around with the new multivariate conditional simulation tool, we found it was working quite well, so we proposed to use that to model the deleterious variables. And then with that, we can investigate the issues related to variability over various time and spatial scales. We can look at the complex interrelationships among the variables as they are preserved throughout the modeling process. And bands of uncertainty in the feed assays can be derived probabilistically to assist with process planning. There's a lot on this slide, and each of these topics will be covered in the subsequent slides, but this is basically just to give an overview of each of the steps that we went through in this simulation process. So first of all, validating the input data, then using the multivariate exploratory data analysis to define the domains, then model the domains, then define a process and the validation steps, then test grid node spacing, set up the test area for each domain, rotate all of the data into an orthogonal workspace, apply the multivariate transform and validate that, model variograms, run test simulations and adjust the variograms iteratively, check the multi-Gaussian property has been maintained, also check the univariate stats have been reproduced in 3 of the realizations, then check the multivariate relationships have been reproduced in 3 realizations. Then once we've done all of those checks and we're happy with what we've got, then we apply the test area parameters to the full simulation space, which was too big to run in one simulation. So we broke it up into manageable chunks and ran 50 realizations on each of those. Then we exported all of that data from Supervisor into DataMine for validation and post-processing. So first step, validating the input data. The input data was incomplete for the deleterious variables. And so for example, we had a lot more samples of sulfur than the other ones. So we decided to delete any intervals that did not have complete assays for all 5 variables. So this ensures that the interrelationships between the variables can be confidently characterized and maintained throughout the process. We use multivariate EDA to define the domains. this was done outside of Datamine and Supervisor. We basically ran a Gaussian and leveling transforms and then applied self-organizing maps and k-means clustering to come up with domains that that separated out the data into, in this case, there were 5 different domains that are as self-similar as possible and also as distinct from each other as possible. And so what we're looking at here is the box plots for each of the variables, colored by the self-organizing map clusters, which I'll refer to as domains from now on. And you can see, hopefully you agree that each of the domains has quite distinct values from each of the other domains. And another way that we used to validate this output was on principal components analysis biplot. So here's an example of one of those. The samples are represented as points on the plot and colored by the cluster that they belong to. And the vectors on the graph represent the variables. The length of the vectors are proportional to the variability of the 2 displayed principal components, which are the 2 axes in this case. And the direction of the vector and proximity to the samples indicates how heavily the sample position is influenced by that variable. So we can see from the graph, for example, that sulfur and iron are highly correlated with each other. Arsenic is also related to sulfur and iron, probably due to arsenopyrite. And total carbon is pulling the data in the opposite direction in this space, which maybe means that there was maybe carbonate that was replaced by the mineralizing fluids, or the sulfides, I should say. And we can also see that organic carbon is doing something completely different. So we interpret this to mean that the total carbon and the sulfur, iron, and arsenic are related to mineralization, whereas the organic carbon is possibly related to lithology. And those clusters weren't just random noise in the drill holes. When you plot them up, they actually hang together as different groups that we could model successfully. And so we did that in 3 dimensions. And that became one of the inputs to the conditional simulation process. You're not supposed to be able to read this slide, that's okay. It's just, I wanted to show how we planned the process and all of the steps that we were going to follow and how they related to each other before we started. And this was an ongoing thing, but it really helped when we had 3 different people working on the project to communicate the process and make sure that we were doing only what was necessary, because there is a lot of work to do and trying to be as efficient as possible. But just to kind of highlight some of the things here. So in this column here, we have the preparation work that we did in Datamine. In this column, we have the simulation and validation work we did in Supervisor. And then here we have the validation in Datamine and the post-processing in Datamine. And then vertically, it's separated into the test area, and then below that, the full simulation space. And just to zoom in on this a little bit, you can see that there were some tests that we ran that were feedback loops. So we do something, we check it. If it's not okay, do it again until it's okay, and then go to the next step, run through several cycles of that until we're happy with the parameters, etc., before moving on to the next step. So the next step in the process was testing the grid node spacing. We ran various trials and we found that with a grid node spacing of 1 by 1 by 1 meter, we had the best reproduction of the variograms and statistics. And so we went with that. However, looking back on it now, I would have tried harder to use a bigger grid spacing because the files that we produced were enormous. So we're still working out a process to try and optimize that. Trying to get, if you have a smaller grid spacing, you get better reproduction of variograms and stats, but if you have a bigger one, then the processing is much faster. So we're working on that at the moment, how to find that sweet spot. Then we set up the test areas for each domain. So the idea with the test area is that you work on a subset of the data that is densely sampled for the particular domain that you're interested in. It's large enough to be able to get meaningful variography, and it's small enough to assume stationarity and to run the test quickly. We didn't want to do all of our test work on the whole domain because it would just take too long. So we have, of the 5 different clusters, you can see that we've chosen different test areas based on the amount of sampling that was available for each of those clusters. Then we rotated all of the data into an orthogonal workspace. Based on my experience with conditional simulation and data mine, I've found that even if you have a domain that's only separating out part of the space, when you run the simulation, the simulation has to visit all of the grid nodes in the block model prototype that you give it. So if you have something that's striking 58 degrees azimuth, then you're going to create a lot of points in the block model prototype that are basically useless, unnecessary. But if you rotate it, then you can make the prototype a lot smaller. And so that's what we did there. And you can see the output on the right-hand side. Then we applied the multivariate transform and validated that. So the original 5 variables were transformed into the variables F1, F2, F3, F4, F5, which all happens inside Supervisor. And in the process, they have the original relationships removed. They are decorrelated. We use the GPCA transform. There's 2 options in Supervisor. We used that one. The other projection pursuit transform wasn't working at the time. We only had the beta version available. But anyway, the GPCA consists of iteratively applying principal components analysis and marginal Gaussianization to minimize the total multivariate correlation. So you can visualize that as making a meatball. So you pull off a randomly shaped piece of meat and then you squash it and you rotate it and squash it again and rotate it and squash it again and again until you have something that's spherical. And that's basically what the transform is doing, but to the 5 variables at the same time. The transform also stores the original relationships among the variables so that their values and relationships can be restored in the original units at the end of the simulation process. And if sufficient iterations are run, then the transform ensures that the input variables for the conditional simulation are decorrelated and multivariate Gaussian, which is some of the underlying assumptions of the method. Visual validation showed that the transform had successfully Gaussianized the input variables and that their bivariate relationships were also Gaussian. So what we're looking at on the right-hand side is a series of scatter plots plotting each of the variables against each other, and we can see that the distributions are approximately round. That's the different colors are representing the density of points. So we thought that that process was successful. Next is model the variograms, and that's all pretty straightforward, so I'm not going to spend any more time on that. But the next step was a little bit more complicated. So an experimental variogram of an output realization must reproduce the original reference variogram model satisfactorily. And that doesn't typically happen without some manual intervention. So our approach was to first run one realization and check the variogram reproduction. So you basically bring that simulation output back in as data and then run a variogram on that data to check how the variogram produced from that simulation matches up with the original input variogram model. When you do that, you can see that sometimes, maybe you could model the variogram a little bit differently, and that might agree better with the simulation, which is, it sounds a bit circular, and it is, but the input variogram and the simulation kind of feed off each other, and so you can usually improve it a little bit if you model the variogram a little bit differently. But then that's usually not enough. So you might not still have good agreement between the input variogram and the simulation. So in that case, we then moved the ranges of the input variogram until we got satisfactory reproduction of the original reference variogram with the simulation output. And I'll try and explain that better with the next slide here. So if we take, for example, the original reference model is the solid red line. the first simulation output is the red dotted line, and it doesn't agree very well with the original reference model. So then what we did was adjusted the input model. So in this case, we moved the ranges out, and then we rerun the simulation, and then the output of the second simulation does match up with the original reference model. And so with that adjusted model, we ran the simulations so that we could reproduce what we believe was the original reference model. And there's some examples in the little inset there of some of the simulation outputs plotted as the experimental variogram with the red dots, and the models, the original reference models that were used for each of those variables. Then we wanted to check the multi-Gaussian property has been maintained, and this is just a standard output from Supervisor. So on the left-hand side, we're looking at the input data, and on the right-hand side, we're looking at the simulation output. And again, each of the variables are plotted against each other, and if we have circles representing Gaussian distributions in those 2 dimensions, then we're happy. That's a good result. Next was to check the univariate stats had been reproduced. And this was, when we saw these plots, that's when we really got impressed with this tool, because it's running the simulation like this with the multivariate transform seemed to produce a better result than just doing a univariate simulation for some reason. Maybe all of the transform and all of the variables being modeled simulated together kind of helps it somehow, but we found that the output was excellent. Here we're looking at arsenic in the original units, not Gaussianized anymore, and the standard validation output from Supervisor. So swath plots across the top in X, Y, and Z directions. Then we have a histogram, log probability plot, and the QQ plot. So hopefully you agree that we had pretty good agreement between the input data and the simulations. This was just one of the realizations, and we did it for 3 of the realizations to check how much it was differing for each realization. So this is arsenic, this is organic carbon, this is total carbon, and total iron. I'll just go back to total carbon, and we can see that you might look at this and think that this isn't domained very well, because we have over here in the X direction swath plot, we have quite clearly 2 different populations. In the center, it's related to the mineralization, and around the outside, it's lower carbon. And the simulation has tried to reproduce that, but there's a bit of smoothing around the edges. But even so, when you consider all of the different variables that have been modeled here together, and that the domains are not just using total carbon, they're using all of the variables to generate a domain that's internally coherent. That's why we have sometimes these boundary effects or things that don't look like a very good domain. But in spite of that, I think that the simulation's done a pretty good job of reproducing the input data. Even in the case of these at least 2, maybe bimodal, maybe trimodal population, it's managed to reproduce that. So we're pretty happy with that result. And then checking that the multivariate relationships have been reproduced. So we're looking at here a scatter plot matrix, and these are the variables plotted against each other: organic carbon versus arsenic, total carbon versus arsenic, iron versus arsenic, sulfur versus arsenic, total carbon versus organic carbon, iron versus organic carbon, sulfur versus organic carbon, iron versus total carbon, sulfur versus total carbon, and sulfur versus total iron. And on the bottom, it's basically a mirror image of that. And then we have the log probability plots for each through the middle there. So you can see that there are some complex relationships that needed to be preserved. Where I have the mouse right now, we have a linear correlation between sulfur and iron, but some of these more complicated relationships between total carbon and organic carbon, we wanted to try and reproduce that as best we could. So this is the input data for this particular cluster, and then this is the simulation output. You can see it's done a good job of reproducing this linear correlation here. Some of these more complicated relationships, it's done a fairly good job of reproducing. We were happy enough to proceed with that anyway. But yeah, I mean, it's had a tough challenge ahead of it. So we're pretty happy that it's done as good a job as this. I'll just switch between the two so we can see the differences. So that's the input data, simulation output. I should have mentioned also that what we're looking at here is a point density. It's colored by point density. So where it's hotter, there's more points. Where it's cooler, there's fewer points. So we want to see the hot spots line up with the hot spots, which is mostly happening. We can also see that there's some kind of stepwise output in the transform, and I'm not sure why that is yet, but maybe with a bit more research I will understand that. So then we were happy with the reproduction of the multivariate relationships, and we continued on. So once we had our simulation parameters for the test areas, we then applied it to the full simulation spaces, which is what you're looking at here. And we had to break it up into manageable chunks because there's two reasons. If we do that, then we can run the simulation with multiple instances of supervisor at the same time. So we can run, for example, areas 1, 2, 3, 4 at the same time, and it works. So we could get through it faster. And the only drawback of that is that you produce so much data on the hard drive that you need to spend the rest of the day getting it off the hard drive so you can do the next set of simulations. But yeah, the amount of data that we were producing was pretty incredible. I think we ended up with 2 terabytes of data after we zipped everything up. This is some of the outputs, and sorry that it's not complete. This is just something that I had available, so I dropped it in there. But you can see that we've got some of the domains populated with simulations here. This is obviously a high sulfur grade domain. This is a low sulfur grade domain. And then we have some intermediate sulfur grade domains in here. And the input data here is represented as these darker spots. And the simulation is filling the space in the background. You can see it's a little bit darker here because we have the, there's 2 different areas or 2 different chunks of data where we split it up. And this is where those 2 chunks are overlapping. So I'm going to flick between this realization and the next realization, and you can see how the 2 realizations differ. So that's 1, 2, 1, 2, 1, 2. And in cross section, it's 1 and 2. You can see that high sulfur grade domain in the middle is also highly variable, which is kind of what you expect. So that was good. And then finally, the post-processing. The imported, well, first of all, we exported the results from Supervisor into Datamine, and that was at 1 by 1 by 1 meter resolution. We can use that information directly in further studies, or we can also post-process it using the CS model process in Datamine, which produces a whole lot of stats from all of the realizations, mean, median, everything you expect, plus it produces the percentiles that you tell it, and also proportion and grade above cutoffs. We summarized those 1 by 1 by 1 points into 5 by 10 by 10 meter parent block sizes, and that reduced the file sizes enough to allow the clusters and sub-areas to be combined into one block model. And the statistical summary block models were produced with a regular block size. So then you saw that we had each of the simulations were run on different domains, which were all stuck together. So we had regular block sizes. We needed to then sub-block that so that the clusters could be stuck back together again with no overlaps. And we just did that by filling each of the wireframes with sub-block models, stamping that statistical model onto the sub-block model, deleting the bits outside the cluster, and then we could add them all together. So finally, the outcomes, the block models and post-processing macros were supplied to the client, who are currently interrogating them for the upcoming mine plan. The project has led to a training program for the client resource geologists with the aim of for them to update the future conditional simulations. We're still faced with the challenge of using the large output files in a production setting, and again, working out if there's a way that we can have a larger grid node spacing and still get a satisfactory result. And we're also looking at efficiency enhancements so that the simulation process can be integrated with the design process. So the client was very happy. We're really happy with the result as well, and pretty impressed with the new tool available in Supervisor. That's about it.